9.1, Vectors and Dot Product. 8.3 and 8.4 in your book. Some quantities like speed have a magnitude, like 50 miles per hour. And some, like velocity, have a magnitude and a direction. So 50 miles per hour northeast, right? So there's a difference. When we say speed, we just say maybe we can represent it by 50 miles per hour. We don't know where, in what direction, but velocity says 50 miles per hour northeast. So it's definitely in this direction, right? Not any other direction. Right. Okay, for these quantities, it's sometimes useful to use vectors, right? That's these types of arrows that I'm drawing. In this section, we're going to study the geometric and algebraic properties of vectors, and then we're going to apply our knowledge to real-world problems. All right, it's just like with trig functions, it's very important to make sure you sketch what you're doing. And then we're going to also learn the law of sines and the law of cosines, two very important rules. Another thing you should focus on is the dot product. And you'll see what I mean when we get to that. Okay, so we call quantities with no direction, like speed that we talked about just now, scalar quantities. So that's just numbers that, for the most part, we're not going to call vectors. Other quantities with direction are called vector quantities, and their magnitude is the length of the line segment used to represent them. So for example, if we say we have a car that goes 10 miles per hour northeast, then this length for we can say it's 10, right? 10 units long, right? And really what we mean by that is that if we have another car going 20 miles per hour northeast, then that length should be twice as much, so 20 units, right? Okay, two vectors are equal if and only if they have the same direction and magnitude. So if we have 10 miles per hour northeast and 10 miles per hour northeast, then those vectors are equal. But if we have 10 miles per hour northeast and 10 miles per hour southwest, those vectors are not equal. The sum of two vectors is also another vector, and we call that one the resultant force. The resultant force. And there's two ways to add vectors. You can take one vector, let's call this one A, and you can add it head to tail. So you can add the head of one to the tail of another one. So let's say this were A plus B. And the resultant vector, or the resultant force, would be the line connecting the tail of A to the head of B. So this would be A plus B. And that's what we would call the resultant force, that vector. Or we could use the parallelogram rule. Same one, A. And instead of saying B is over here, we're just going to take B to start off in the same spot. B starts off here. And then what we do is we create a little parallelogram using both a copy of A and a copy of B. And we say that's the resultant force. That's A plus B. It's up to you which one you prefer better. For every vector, there's also a negative vector. For A, there's a negative A. And all we mean by a negative is that it's in the opposite direction. The law of sines and law of cosines is going to be very helpful to solving vector problems, so we go over it now. If we consider the triangle with sides A, B, and C, and angles A, B, and C, It doesn't have to be a right angle. It just be any triangle. Sorry, it doesn't have to be a right triangle. Just any triangle. Let's say that's A, that's B, and that's C. A, B, C. Then the law of sine says that the ratio of the sides to the sines of the angles have to be the same. So sine of A, remember this has to be an angle in here. It has to be big A, it can't be little a. Over little a is equal to any of the other ones, sine of B over B, or sine of C over C. And these are just ratios, so it doesn't matter how you write this. You can say B over sine of B has to equal whatever you want, A over sine of A. Okay, and etc. We're going to use that property to solve lots of different triangles and vector problems. The law of cosines is very similar. Same triangle here. We have A, B, C. B, C, A. And this says that if you're trying to find one of these angles, usually we say we're trying to find, one of the sides. C. Let's say we're trying to find little c. We can use something that looks like the Pythagorean theorem. C squared is equal to, we use the other two, A squared plus B squared, kind of like the Pythagorean theorem. But then we have an extra bit because this is not a right triangle. It can be any triangle as long as it's possible. Minus 2 times A times B cosine of C. So you need that extra little bit. Negative 2AB cosine C. Notice the order. A, B, C. Okay. So let's try this in a problem. We're going to use the law of sines or cosines to find the length of the following resultant force. So we have 11 pounds of force, which can be represented using a vector, and then 5 pounds of force. And let's make this one a little bit shorter actually, just to be a little bit more clear. 5 pounds of force, and it's 45 degrees in between them. And let's use the parallelogram rule here. So we're trying to find this resultant force right there. How can we do that? To be okay, the first thing we have to do is notice something that we haven't talked about. But notice that if we were to extend this line a little bit this way, and remember that this is 45 degrees, what does that tell you about the rest of the way over there? Remember, that needs to add up to 180 because it's a straight line. And that should be 135 degrees. And this angle right here is the same as this angle right there. Right? Because that's 11 pounds, and that's just a copy of the 11 pounds. So this is 135. Likewise, if this is 135, then what do we know about this angle right here? That's also 135. And what do we know about this angle here? That's 45. All the way across is 45 degrees. Right? And what are we trying to find? We're trying to find this length right here. So we can use the law of sines. We can call that length C. And say C squared is equal to A squared. Let's say that this is A right here. And that's B right there. So it's equal to A squared, or what is this length right here? 5 pounds. Plus B squared. What is this one right there? 11. Minus 2 times A, 2 times 5, times 11 times b times cosine of c. Cosine of c is just the opposite of c. It's 135 degrees. So that tells us that this has to equal c is equal to the positive square root of 25 plus 121 minus, what is this, 2 times 5 is 10, times 11 is 110, cosine of 135. Right. You can use technology to figure out that answer. The part we want to focus on right now is just setting that up. And that would be the resultant force. Find the force required to keep a 50-pound wagon from sliding down a ramp inclined at 20 degrees to the horizontal. So let's draw this out. This is a lot to try to do in your head, so we need to draw it out. So there's a ramp. There's the ramp we're talking about. It's 20 degrees inclined. We have a wagon up here somewhere, let's say. It's 50 pounds, so the force, like the weight or the force in the downward direction, is 50 pounds. And we're trying to find the force required to keep it from sliding down the ramp. In other words, here we have another force, and this is from physics, but I'm telling you this now. You'll have to use this on your homework. We have another force, which is the force of the wagon itself pushing down on the ramp. So completely perpendicular to it. Pushing down. And we're trying to find this force right there. It's not quite drawn correctly. It needs to be kind of parallel to this ramp. I'm just a bad artist. The key to this problem, though, is to notice that this angle right here is also 20 degrees. Okay, so let's make a little picture of that triangle. This angle is also 20 degrees. Make a little bigger picture over here. We have 50 pounds. We want to find this force, the force that's going to push in this direction. In the opposite direction, since the wagon is trying to slide downward, we want to find the force that's going to push upward. It's called a friction force. Let's call it X. How can we find X? This is a 90-degree angle. Okay, this is not as difficult as the last problem, actually. Here we're going to use the sine of 20 is opposite over hypotenuse, is x over 50. So that tells us that the force at x is going to be 50 sine of 20 degrees. And that's it. We're done. Some algebraic properties of vectors. We can place vectors on the coordinate axis, x and y, and label the terminal point AB. So here, starting at the origin, 0, 0, and let's say that point right there is A, comma B, right? And then we can draw a little arrow there to represent a ray or a vector. And now that we're talking about a vector, to talk about this entire vector, not just the point AB, but the vector, we're going to use brackets, A, B, to represent the vector. The magnitude of the vector is just the length of that vector, right? So the length of it is given by the distance formula, just like you would think. And if we call this vector u, then the distance of u is equal to the x coordinate, which is a, squared, plus the b coordinate squared. Right? That's from the Pythagorean theorem. A squared plus b squared is equal to c squared. So we're going to take the square root. And the angle of the direction, this theta here, is actually going to be given by tangent. Tangent of theta, you know, is opposite over adjacent. So it should be b over a. So if we have a vector, for example, the vector 3, 4, in other words, that says you travel in the x direction 3 times, then you go up in the y direction 4 times, and that entire vector is what we want to focus on. What is the magnitude? The magnitude, let's call that vector v. Sometimes we call it u, sometimes we call it v. Then the magnitude of v is the square root of a squared plus b squared. 9 plus 16 is 25, so it's the square root of 25, which is 5. And tangent theta, because this is 4 and this is 3, is 4 over 3. So to find theta, we would need to do arctan, or tan inverse if you're using your calculator. Tan inverse of 4 over 3. Horizontal and vertical components of the vector u are given by a is equal to the magnitude of u cosine theta, and b is equal to the magnitude of u sine theta. So as an example, if we knew from like our last example we just did that we had a vector with a magnitude of 5, in other words, we knew that distance was 5, but we didn't know what that point was at the end. We didn't know the x and the y values. And we knew that this angle theta was about equal to 53.13 degrees. Then how can we find the x component, which we're calling a now, and the y component, which we're calling b? Well, for find x, all we're going to do is use a is equal to the magnitude, which is 5 cosine of 53.13 degrees. And to find y, it's 5 sine of 53.13 degrees. So cosine should make you think x, sine should make you think find y. Try those values, see what it gives you. Operations with vectors. If we want to add two vectors, and let's say we have them in the form a and b, and another vector c and d, in other words, we have their x and y components, then we just add the x's with the x's, a plus c and b plus d. Add x to x and y to y. If we want to multiply a vector a comma b to some number c, some scalar number, then we just multiply the scalar on the inside. So we make everything c times bigger. So it should be a times c, b times c. So it makes the vector that much longer. A unit vector is a vector with magnitude 1. And there's two standard unit vectors. The vector I, which is just the horizontal component. So this is 1 comma 0. So on the x and y axis, the vector I is just the one with an x value but no y value. 1, 0. And it has a length of 1. That's why this number is 1 here. That's why it's a unit vector. And the other common one is j, is what we call it. And it has no horizontal component, but it has 1 for the vertical component. And it looks like this. Okay. Because this I and that j just have horizontal and vertical components, we can write any vector as a combination of these two standard vectors. So if we wanted to write the vector 4 and 5, that would be, for example, 4 times I plus 5 times j. Because 4 times I is 1, 0, and 5 times j is 0, 1. So we can multiply these inside. 4, 0, 0, 5. We can add them, the x's to the x's. 4 plus 0 is 4. 0 plus 5 is 5. So we can make any vector just using I and j. The dot product of two vectors AB and with components AB and CD is just the product that multiplies the x components and the y components and then adds them together. So as an example, if I were trying to find 3, 4 dotted, this is dot, with 2, 1, it would just be, and this is not a vector actually, this would give you a number, 3 times 2 plus 4 times 1. The x and the x and the y and the y. And then you add them together. 6 plus 4 would give you 10. That's the dot product. Moreover, the dot product is also used in this following equation here, this following formula. Cosine theta is equal to the dot product. Right, for two vectors, let's say that's u and that's v. U and v. Usually the symbol means a vector is what we're dealing with. Cosine of theta, where theta is the angle between them, is equal to the dot product divided by the length of each one multiplied to each other. And we'll use that in an example here soon. So try these on your own though. Let's see if you can figure them out. Find the angle between -1 and 2 and -3 and 6 vectors. So let's draw this out on the x and y axis to be precise. -1, 2, that's that first vector, -1, 2, -3, 1, 2, 3, 6, 1, 2, 3, 4, 5, 6. That's the other vector. Let's say we wanted to find this angle right there in between them. You can barely see it. How would you find that? So the easiest thing to do, instead of trying to figure it out by measuring it or something because it's so small, is use cosine of theta to be the dot product. So -1, 2 dotted with -3, 6, and then find the magnitude. The magnitude of this is square root of 1 squared plus 2 squared, or -1 squared, which is the same. The magnitude of this other angle is square root of -3 squared plus 6 squared. This is 1 plus 4 is square root of 5. This is 9 plus 36 is 45, square root of 45. Which is 9 times 5, which is 3 square roots of 5. Okay, let's see what the dot product would be. The dot product of -1. So let's put that in the bottom here. Square root of 5 times 3 square roots of 5. The dot product would be -1 times -3, or 3 plus 2 times 6 is 12. Here the square roots cancel, so I'm left with just 5. 3 plus 12 is 15 over 15, which would equal 1. So this says cosine theta is equal to 1. And to find theta, all you have to do is find the inverse, cosine inverse of 1. See what that gives you on the calculator. But before you do that, try to ask yourself, when is cosine theta equal to 1? Remember? That was when we had the point 1 comma 0. In other words, the degree, the angle was 0. So this is actually, it looks really small because there's actually nothing there. It's the same, there's no angle, it goes through the same point. Another way you could have noticed that, so this should be 0. Another way you could have noticed that is that negative 1, 2 times 3 is negative 3, 6. So this one is the same vector, only 3 times as bigger. So there shouldn't be an angle in between them. Find the resultant vector u for a vector u that has a magnitude of 12 and a vector v that has a magnitude of 20, and the angle between them is 27 degrees. So 12, 20, the angle between them is 27 degrees. We did a problem like this earlier. We're trying to find the resultant vector. We know if this is 27, then this is what has to add up to 180. So it's 180 minus 27, 153. This has to be 153 also. To find this angle, we need to use the law of cosines. Let's call that C. Let's call that A. Let's call this over here B, which is 12 also. C squared is equal to A squared, or 20 squared, plus B squared, 12 squared, minus 2 times A times B cosine of C. And then take the square root of all that. 20 squared plus 144 minus, what is that? 24, 480, I think 480 cosine of 153 degrees. And simplify that, and you'll find your answer. You're now ready to start homework section 9.1.